Okay, so today I don't have a next week one to announce, so we'll start right in. So we have Dr. Koiter here. He's been here for
Since 2017?
2017.
No,
Oh
17
my
or 18.
goodness, time flies. I was going to say 18.
I think I'm on year 6. Well, I must be because I'm on
Oh, you're on
sabbatical.
sabbatical, so you're on year
Yeah.
6. Yeah. So Dr. Koiter is associate professor in the Department of Geography and Environment here at BU. His research program focuses on how interactions between land and water management practices and geomorphology affect soil and water quality. And with his research group, he investigates a wide range of agricultural issues, including soil erosion, downstream sedimentation, nutrient dynamics, greenhouse gas fluxes, and extremes of moisture. And with that, I will let you take it.
Awesome. Thank you for that. I will tell you nothing about any of those things today. So today is a bit more of a philosophy in how to do science in a bit more general terms. And it can be any type of science. It doesn't have to be the natural sciences or physical sciences. It applies to the arts. It applies to English. It applies to the humanities, right? I'm going to take it very much from a soil science perspective, because that's kind of my jam. So you will hear a little bit about soil science in it. And what I really want today to be is just basically an exploration of these themes. And we're going to talk a little bit about what open and reproducible science is and isn't. What are some of the tools available? Why are some of us really good at it? Why are some of us really terrible at it? And I'm by no means perfect. And so I'm going to show you lots of cool things I probably should be doing, but I, in fact, don't actually do them. And so I'm also going to be showing you a couple of some examples from my own work that have what I would consider to be some successes. And again, I just kind of hope this kind of just generates some thought and some ideas. So before we get started, as a soil scientist and anyone in the natural sciences and other disciplines, right, we focus on the health or the function of soils, right? So we work, we learn, we educate on traditional territories, and the land and water that we appreciate so much also includes the histories of its people, and oftentimes the history is not a particularly pleasant one. So it's always kind of important to kind of remember that as we're kind of doing some of this work. So with that, Brandon University and the surrounding area, some of which includes my research sites, is the traditional homelands of the Dakota, Anishinaabe, Oji-Cree, Cree-Dene, and its Métis people. All right, so here's an outline of my talk today. So we're basically going to talk from everything from collecting your data all the way through to data analysis, all the way through to its end product, which is usually some type of form of communication, whether it's a presentation or a journal article or just talking to your friends, or whatever the case may be. It doesn't really matter. That's usually the end goal of research, right? Is to disseminate it. And we can be open and reproducible in every single step. All right, so let's start a little off with some definitions. So first off, a bit of a difference between reproducibility and replicability. So I'm going to be talking about reproducibility and not replicability, which is a bit of a mouthful. So when I talk about reproducibility, right, I'm really talking about data. So if I were to give you the data set, you should be able to replicate or reproduce what I did. Okay. Replicability says, okay, well, how I designed this experiment, I did my analysis, these are the results, these are the conclusions I came to. You should be able to do that, a similar type of experiment, and you should come to similar conclusions. Your data might be a little bit different because you might be in a slightly different area or you're sampling a slightly different way. But in the end of the day, we should come to the same, have the same results and the same conclusions. So when I talk about reproducibility, I don't actually care whether or not the results are correct or not. That's kind of its own thing, right? It's really more about understanding, being transparent about what you've actually done, right? And this is really important if you have a very large and very complicated data set, right? If you have a very small, very simple, being reproducible is actually quite easy. But if you're doing a lot of filtering of your data and a lot of complex analyses and stuff like that. This is really where it comes into play. So what about open data in science? We talked about reproducibility, so we can also talk about open data and open science. And so this is all about making your data, your methods, and your interpretation available, accessible, transparent, and reproducible, okay? And it can be a challenge to actually hit all of those, right? And for various reasons, which I'll get into in a little bit. So why do we care about reproducibility? Right, first off, it allows us to evaluate the data and analyses and the models on which conclusions are drawn. Right, so you read these papers, they have these really complicated stats, right? But there's probably a lot behind the scenes that you don't necessarily see, right? Especially if you have a model, there's often parameters that you have to set. And so sometimes those parameters, they're not actually reported in a paper, right? So it's not actually reproducible, right? Because of that, you don't actually have all the information. It allows you to revisit your own work. And this is one of the reasons I really love it, right? So I can have my data analysis, and as many of us do, I push it off the side of the desk as I work on something a little bit more pressing. I can go back to it, and actually you can just follow my steps, and it doesn't take me as long to kind of get going again. Or you're like, or you have a supervisor like me, it's like, oh, did you consider just doing this? Right? So instead of trying to reinvent what you just did, you actually have a really good record of what you've done. You can incorporate it in. You can do an easy comparison and say, oh, it doesn't actually matter. We came to the same results or the same conclusions, so it's not all that important. Right, so let's talk about why it can be difficult to reproduce. So probably the number one is the data is often not made available. Right, so again, I could have the most reproducible science, but if I don't actually give you the data, you can't actually reproduce it yourself. Method sections, so I kind of talked about them. They're often terrible in most papers, right? Especially journals that have word limits. What's the first thing you're going to cut? Your method section, right? You're going to put down the bare basics, right? And if it's something that you're new to or unfamiliar with, I'm always looking for like, okay, well, I have that same instrument, but I have these 8 options, but you didn't tell me what to select for these 8 options, right? So I can't actually reproduce it. Graphical programs. So oftentimes you have drop-down menus. How many of us actually document, oh yes, I went to here, to here, to here, to here? Because again, we're selecting options as we go along. So unless you write them down, it's hard to reproduce it, right? And the last one is not making your code available or open, right? So if you're an R user, or you're a Python user, or a MATLAB user, right? You're doing these things programmatically. And so again, sharing your code is a really great way to make it reproducible. All right, so let's talk about kind of the very first step in science, right? Which is usually, well, after experimental design, right? You actually get your data. And, right, especially in the natural sciences, right, we have data loggers. So, Pete, what interval do your water levels log at? So 15 minutes, and you have a long-term site. So it's been going, what, for like 5 years? So 5 years times 15 minutes times how many wells and sites you have, right? That is a buttload of data, like huge. I'm pretty sure Excel would die if you tried to import it. So 105,000 rows for our on-campus weather station per year, right? Right, so this is not like something that many of us encounter, right? So documenting and how you get and download or import your data is really important. Especially a lot of us will actually start to use publicly available data. So I use weather data a lot, as many of us will probably do, and we usually go to things like Environment Canada. And again, you can go to their website and click and click and click and click. But again, if you don't actually document all your choices, it's hard to reproduce. All right, so a little plug for WeatherCan. Right, so this is an R package that I can actually access and download data. And because it's scripted, I have a record of it. Exactly what stations I've asked for, what time intervals, all that information is there. I will never forget. Or if I do forget, I can just go look it up. And one thing I always try to impress upon my students, and I encourage all the grad students in here, is as soon as you get your raw data, duplicate it and archive one. Don't overwrite your data. Don't overwrite your data, right? And so I do the same thing. It's just like, again, I do everything programmatically. So I have my raw data. And every time I make a change, I actually just update my script, but it's always referring back to my original unmodified data. All right, working with large data sets. So yes, we have these 100,000 rows or whatever the case may be. So now you got to format them, right? Because your logger, I'm certain, has probably nonsensical headers, right? You may have to merge data. So I want data from this site and this site all together. But again, your columns may not necessarily quite overlap perfectly, right? So there's, again, how do you merge your data sets? What are you merging by? Is it by year? Is it by site? How did you combine them? Quality assurance. Again, another thing I try to impress upon my students, there is a very big difference between an NA and a zero. Right? An NA is just missing data. A zero actually means it's zero. And so when you're going through your data and you have zeros, are they actually NAs? Or your NAs actually zeros? In some cases, they actually are, right? So again, you have to make those judgment calls. And again, you need to have a record of it. Yes, I set all the NAs to equal 0, right? Another one I run into quite a bit is things like detection limits, right? So I end up with a data set that has, less than 0.01. Stats with not whole numbers is really difficult. You can do it. But again, there are ways of kind of getting around it. So people use half the detection limit, or they'll use 0 or some other things. So again, if you're going to do something, you need to document it. Outliers. Do you keep them or do you throw them out? Again, the outliers are one of these things that always scares me in terms of like, do I remove it or not? Right? I always ask myself, is this actually good data and just abnormal and it tells me something really interesting? Or is it just an instrument error or like a transcription error or something like that? Right? So there are reasons to throw it out and there are reasons to keep it in. So again, right, outliers in terms of how you deal with them is very important to keep track of. And lastly is typos and errors. So a common one I have is site with a capital S versus lowercase s. So site 1 and site 1. Are they actually the same site? Yes, maybe. No, I don't know. So again, if you document it, it's like, yes, I combine them as to one site, right? That's why it's important to know. All right, so now we have this nice data set. We're formatted. We've dealt with all the outliers, errors, omissions, things like that. So the next is, well, if we're going to do our analysis, we're going to make some nice figures. Okay. We may not use our entire data set, so we may actually subset or filter our data set. So what are the thresholds you used? Analysis used. So again, I often say, I'll just use a blankety blank analysis. And then I'm like, my data doesn't meet the assumptions of this model. Let me try this. Someone told me to try this. I try that. And so kind of trying to keep track of all these different things I've done, right, is really important. I've touched on the parameters as well. So if you're using a model, so sometimes you set thresholds for things. Diagnostics. So again, if you're running things like an ANOVAs or other regressions, right, you want to check your residuals and things like that. And so again, how you document that, how you actually check for those things and actually made sure it was good is important to keep aware of. Figure creation process. So depending on what kind of plotting program you're using, right? I think even I think there's 8 different ways to make a box plot. Which one did you choose? Right? I often just use the default because I don't know why there's other methods. So, and then the last one is software versions. right? So R is continually updating, other programs are continually updating. And sometimes it makes no difference, and sometimes it makes a big difference. Again, just keeping track of it. All right, so open data and open science. Why is it important? Improved global synthesis of knowledge. If I put it out there, people can read it, right? People can use it, they can build on it. It makes it more robust and more reliable, right? So I make it open. You can see what I did, and you might be like, hey, Alex, you made a mistake. You use this method, you should have used this one. I said, oh, good to know, right? Better collaboration. I'll touch on a bit of an example later on. So if you work with others. Improves collegiality. So again, if you make things open, right, tend to get along better with your peers. Promotes EDI, so equity, diversity, and inclusion. So this was something that I discovered recently. I never really give it much thought. And I think a lot of it has to come to in terms of the resources particular groups of people have, right? So if I have the resources to build and create a wonderful model, once I put it out there and it's open, anybody can use it, right? They don't need to pour in the resources to actually create it. It's there, right? And it's open. It's not, oh, if you work here or you have to pay for it or whatever the case may be. It's free and open. It's difficult to be open. It can be expensive. Like open publications, they can be an extra like $5,000 or $7,000 American dollars sometimes. It's a huge amount of money. It can be time consuming, right? We're busy. Lacks skills. This is sometimes where I fall into it. I'm not entirely certain how to do it. Or you might be unsure of what happens, right? It does put you in a bit of a vulnerable position to put it out there because there are assholes out there who will say, oh, you did it wrong, instead of saying, oh, here, let me help you, right? They'll drag you through the mud or make an example of you, right? So it does put you in a vulnerable position. Sharing is caring. How to make your data open. So there's lots of different ways of doing it. So you got to consider, like, where do you host it? When to make it available. Do you make it available before you publish, after you publish, 5 years after you publish? I don't know. Removing sensitive data. So if you work with people, you'll want to strip out their names, addresses, and things like that. If you're working in sensitive ecosystems, you may want to remove things like GPS coordinates. So if you're working with an endangered species, you don't want people to know where these things are, right? So you can remove some of these things. Format. So it might be an Excel file, it might be a CSV, it might be a map, whatever the case may be. And then for how long do you keep it available? You can definitely, so these are some of the questions that I've been kind of thinking about and trying to figure out what to do. So here's an example of a repository. And so for anyone who's working on greenhouse gases, right, there's this FluxNet. And so you can actually put your data in there, and it allows people to basically do larger scale modeling and start to look at the bigger picture, because now it's just like, well, I have this data from here in Manitoba, but also here in BC and wherever else, right? So you can start to put it together. Or I measure for these years, you measure for these years, right? All these types of things. So publication as well. So there's lots of different ways and models for kind of open access. So there's open access, which means you don't need to have a subscription. So university doesn't need a subscription. You don't need a subscription. Or you can get around it by sometimes posting preprints, which is one of those kind of like, think you're allowed to do, but I'm sure publishers don't love it. Even the peer review process is often not very open, right? Most peer review is double blind. So I don't know, or not necessarily double blind, at least single blind, right? I know who the authors are as a reviewer, but they don't know I'm a reviewer. Right, so there is a shift to saying, okay, well, let's sign your reviews. Let's be open about who's reviewing what. And it could be everything. When it actually goes to publication, you actually publish the peer review process as well. The nice thing about that is it makes people nicer, right? They can't hide. They have to be a bit nicer. They can be firm and they can be, right? They can have their pet peeves and opinions, but they can't, call me names type thing. All right, have detailed methods, right? This could be even using things like supplementary materials in journals, right? You can have as much as supplementary materials as you want now, right? Because it's just online. Use open source software, right? Because anyone can use it. It's not proprietary. Make your code available, make your data available. And one that I love is study pre-registration. And the way this one works is basically you go to a journal and say, all right, I have enough money to do this experiment. It's going to be designed like this. I'm going to measure this, this, and this, and this. Once I collect the data, will you publish it? And it basically really says, okay, is this a good study, right? It allows to say, okay, well, I did this whole big experiment and I realized that there is no difference between treatments. Like it's one of those studies that, you know, may not go into anywhere else because it's not super exciting, right? So by having it pre-registered, it allows you to basically to have like these non-results type papers, which are important in and of themselves. All right, so why is this, all those great things, so why are we so terrible at them, right? Don't know how, too busy, it's internal, like it's just my own work, so who cares? Worried about being copied or scooped, worried about exposing mistakes, and lastly, you just rig the data, so of course you don't want to be open. All right, don't know how? I encourage you to give it a try, okay? There are lots of supports and tools available, so if you're interested in this, and grad student and your grad program is the time to learn these things, right? It's probably the time where you actually have time to work on these things, right? But it does take time. Too busy? It's typically faster in the long run, right? I revisit my work all the time. Is internal work? It often starts out that way, but often it ends up being shared, right? It may not be shared for publication, it may be shared for other reasons, but invariably it often becomes shared. So, worried about being copied or scooped? In practice, it's fairly low risk. Because once it's open, especially if you properly attribute it, it's really hard to copy and get away with it. People do and people will, but the risk is low. Worried about exposing mistakes? It happens to everybody. And I think this is where it gets back to, you know, putting yourself in that bit of a vulnerable position, right? Every time I submit a paper, I'm scared to death that I've made a mistake, right? And I've even revisited things and been like, oh no, what have I done? And generally it's been okay, but like I do have those, you know, those moments. But again, I think just kind of coming to terms with being open and this idea of like, we can help each other, right? Rig the data. Unfortunately, I think you have much bigger problems. So open data science, it's not going to help you. All right, reproducible analysis. How can you achieve this? Take extensive notes. Pen and paper is pretty cheap and it works. Right? Think about what, when, with what, right? Answer those questions. Do things programmatically if you can, right? So you can write scripts in R, Python, MATLAB, things like that. Version control. So again, you can have versions of your own analyses and things like that. But basically what it does, it allows you to document changes over time. And you can see when you push something, right, you can see what has been changed. And so I've started using things like GitHub, for example, and I can actually track my versions. So it works pretty well. All right, so let's go on to some recent success. So Hassan was a PhD student, now he's a doctorate. He graduated, and he was working on a soil erosion project, and I was helping him out with this. And he was creating some figures with a large data set. And so this says 163,000 observations. All right, so it's not a small data set. Right, so Hassan, he identifies this issue where he has the sites where the percent sand, percent silt, and percent clay don't equal 100. If you're a soil scientist, they should equal 100. If not, you kind of got a problem. Right, so when he was getting 118% silt, he knew there was an issue, right? And so the data is nonsense. And so he requests my help. And because Hassan has a nice programmatic, reproducible data workflow, he sends me his R script and he sends me this data, and I can reproduce the error. Once I reproduce the error, I can actually start to troubleshoot. Turns out some of his data ended up being duplicated. That was all the issue was. He had a site in there that was in there 2 or 3 times. Another one, so I was working with an Ag Canada collaborator, and he asked me to collect some measurements and process some data here in Brandon. So we had a little contract together. And I want to have a reproducible data analysis and workflow as a deliverable. So I've started using Quarto. Quarto is awesome. Okay. I made this presentation in Quarto. Right, and it basically allows me to create these reports. And I basically can have a table of contents, right? And I show them, okay, this is how I read in the data. Here's the code that I use to read it in, right? Right, and I show them, well, this is how I did the calculations, right? And the other thing I did is I actually appended the data to the report. So it is one self-contained document. So he could download it as a CSV and run the script, and he would be able to reproduce it 100%. I also include my session info, so he knows exactly what versions of what packages and what versions of R I'm using. So again, if he doesn't run a discrepancy, we can actually say, oh, is it just a versioning issue? All right, what about open data and open science? Again, there's lots of resources. So one that I'll highlight is called ROpenSci. And so they're a nonprofit, and their entire thing is basically to make open software to basically help people make reproducible workflows. They're great. Open and free software as much as you can. Use GitHub or GitLab, right? So again, these are just places, repositories where you can actually post things publicly or privately. OSF, or Open Science Framework, I'll have an example of that in a second. Fairsharing.org, again, is another repository for data. So again, you can post your data there. Make use of journal supplementary materials, especially now that everything's digital. You can have pages upon pages upon pages upon pages of supplementary materials. Doesn't matter. The other thing is check with your library. They may have a place or a repository where you can actually put your data and actually put other things associated with your project as well. Another thing, maybe not so relevant to the grad students, but for the faculty and for us who apply for grants, when you apply for it, put it in a line for open access publication or other things, right? You want to have time or take a workshop or take a course to learn how to use R or one of these other things, write it into your grant. That way you actually have money to do it. Look for training opportunities and support. There's a lot of it, and I'll do a plug for the R workshop, which is going to be held in February. Sure, I'm pretty sure it is. I think Steffi's online. It'll be happening in February. Yeah, so I encourage everyone to sign up for that. It's a really great experience. Oh, excellent, nice. Encourage it, support it, and try it. So again, even for the faculty, if you're advising people or supervising people, encourage your students to do it. Give them time, give them space. Try to give them some resources to actually do some of this. I think it's a worthwhile endeavor. All right, so another recent success story in terms of kind of open data and open science. So I work a lot looking at measuring soil color. And so we use this little device here, right, to measure color. So basically it measures the reflection. And it basically produces a spectra. So you basically have the reflectance, the Y, and then every nanometer along the X. So again, the output from this tiny little instrument is massive, right? So in terms of taking that data, like the methods, oops, wrong one. So the methods were well established in the literature. Like I didn't reinvent the wheel by any stretch of the imagination. The math is a bit complicated, but not impossible, and it used lots of data. So I had access to a MATLAB script. MATLAB is not free, and so it wasn't really accessible to me. And so I basically worked with somebody who had MATLAB and said, okay, can you just give me the output of different steps in your script, and I'll just replicate it with the same data. And so I basically developed an R script that does the exact same thing, but now in open and free software. So I basically pushed it or posted it to GitHub. So it is publicly available. Everyone in the room can go down there, download it. And I did this because I was just basically emailing my script around. And every time I made a change or found a mistake, I'd then go through my contacts and be like, oh, who's using it? Whoops. Right. So I just posted to GitHub, and people, as they want it, will always have the most up-to-date current version. So we talked about tracking changes. So I do commits. So every time I do a commit, it actually shows what has been changed. So I have this version control. So even comes along with example data. Again, you don't even need to collect your own data. It has a little example for you, and it tells you what you should be getting at the end of the day. I copyrighted it. So it has an open free share copyright. And I even gave it a DOI. So you can actually reference it if you publish with it. And the other really great thing is it's really easy for people to contribute to it. So if people want to extend what I've done, right, they can basically fork it or do what's called a pull request, right? You can make changes and say, hey, will you accept the changes I've made? And I can pull them in, and now it's better, right? And the other really great thing is you can actually open up issues. So if you're using it and you find a bug, right, instead of emailing me, you can actually just post it. You can actually just put in a bug report, which is really nice. Another ongoing success story is I'm working on this wind erosion project, and we're doing some remote sensing of surface properties. It involves a lot of imagery and other large files. So emailing is just not an option here. And what I really wanted, because there's multiple people working on this, is I wanted a central repository where everyone can just dump their data, and that way I have it and can archive it. And so basically right now, it's for, it actually connects to my Dropbox, which is quite nice. And so people can basically just dump their data in, right? There's folder structures and things like that. So it's working not too bad. I can also then eventually link it to my GitHub if I wanted to. As we start to process data, right, we can then post that as well to the OSF. And then we could even work on a publication together via OSF. So again, it basically negates this idea of emailing back and forth, back and forth, back and forth, right? You're finished, you dump it in there, you let me know, I can go there, and I know it's done. So this is the first time I've used it. I'd say it's working reasonably well. It works well for me. It doesn't necessarily seem to work as well for the other people in terms of uploading data. It seems to be a little cumbersome. And this is currently a private repository, so it's just me and my colleagues that use it. So it's not open to everybody, but eventually I may make it open to everybody, right? Or I may make parts of it open to everybody. All right, so some closing thoughts. All right, being reproducible and being open makes science stronger. It really, really does. It can be a little scary at times. One size doesn't fit all. So I showed you some examples that work for me. They may not work for you, and that is fine. You may have your own methods and your own ways, and it will vary between discipline and discipline as well. It is not all or nothing. Anything you do is awesome. Like I mentioned lots of things in here I don't do. Not every project, everything I do is as open and as transparent and as reproducible as I would like them to be. But it is my goal, right? So I always work towards this. It takes time and effort to learn and implement, right? So I learned a lot of this during my PhD, is where I got kind of most of my kind of introduction to it. If I had to learn it all now, I think it'd be much more challenging, just because I have other workload priorities, right? Right. Everybody, even in their private lives, has their own shit going on, right? So it can be hard. There are really great supports and resources available. So there are free courses, Stack Exchange, like all these places where you can go ask questions and you can learn. Yeah. And generally, most people are quite good about responding nicely, right? I find this open science community is typically a friendly community. It can make you feel vulnerable. Absolutely. We will all make mistakes, and it is embarrassing when people pick it up, right? It is. I've certainly done it. However, if you make it open and reproducible, you can actually find your mistakes and actually fix them, which ultimately that is a good thing, right? It might be a bit of a humbling experience, but it is ultimately a good thing, right? Admitting that you made a mistake is not a sign of weakness, right? If you ignore it, that's where the issue is, right? Not learning from them. So with that, I will leave you with a picture of my cat, Nami, the soil science cat. This presentation is completely open and 100% reproducible. If you scan the QR code, it'll bring you to my GitHub page where you can download the Quarto. All the images I use, they're all there. There is also some additional resources I posted to the GitHub as well. So last time I presented this, some people said, "Oh, have you heard about this, this, and this?" And so I've actually just been starting to compile a bit of a laundry list of things. So again, if people have ideas, I will just add to that as well. So with that, thank you so much. I encourage us to kind of have a good discussion about what you're doing, why it's hard, what's working for you. So yeah, thank you.
Thank you very much, Dr. Koiter.
So in terms of like downloading your data and creating a backup copy, I'm assuming Environment Canada never goes into the back end and changes data later, or
I bet you if they find a mistake, they would correct it.
yeah.
However, you probably know when you actually ran the script, right? So again, I think that's what's important in terms of letting people know. It's like I downloaded the data, on this day, or using this, and it is what it is at that day. So you're right, it could change. I think Environment Canada is pretty good. They have a lot of quality controls because I think they don't want to do that. So
Yeah, that's fair enough.
Anyone else? Pete, maybe turn yours off for the moment.
Mine is to commend you on the nice presentation. It was quite interesting. And making data available is actually one of the key things in making data science so impressive. Like in the sites I'm working on a data design, a website design, trying to use some programs like Python. And sometimes I find it so encompassing and I try to use codes. Do you advise that I continue using code? And again, in getting data sets, sometimes, as we said, we have the GitHub, we have other sites. Is data from Kaggle and data from GitHub, are they basically the same, or are there any slight differences in the data sets?
I'm sorry, I'm not certain I quite understand your question.
Okay, I'm asking.
Oh, between like, I couldn't code in Python if I tried. Like, I might be able to kind of figure it out a little bit, but the syntax is very different.
Yeah.
Like if you use SAS or those other like programs, like, yeah, I can kind of read it, but like it'd be a bit difficult, right? It is learning a language. It'd be like me learning how to speak Spanish, right? It takes time, right? But again, Spanish is kind of like French to some extent. Like, some French, Spanish might be a little bit easier. It's kind of like that, right? I think a lot of people, when it comes to coding, is to remember that your computer does exactly what you tell it to do. It is not smart. And I think that's probably one of the biggest things. People are just like, I don't understand why it doesn't work. I'm telling it to do this. And it's like, well, no, I'm not actually telling it to do that. You have an extra comma in there, so it doesn't actually know what to do. Right. So I think that's usually the biggest stumbling block is to basically kind of learn how to do it. And my advice for learning is finding examples that are pretty close to what you want to do. copying and pasting it and then modifying it. Like that's still how I do a lot of things. I'm like, okay, oh, there's an example that basically kind of emulates what I want to do. I'll just switch out the variable names and whatever else. And I still do that quite a bit.
Good. Thank you.
Go ahead, Doug.
It's blue. That was wonderful. I actually invited our grad students in rural development to come, and none of them came, and they should have. Because we had these similar discussions on the human side of things. So
Oh yeah, like this cross disciplines, right?
yeah,
Yeah,
so-
absolutely.
So I do have a soil, kind of a soil versus people question.
Sure.
And it has to do with what's proprietary and what's your contribution in the field. So like in my field, we're increasingly asked to append your survey instruments and things like that we've spent months and months developing and testing over time. And some people are reticent to do that. And so I just wonder if you're just talking about data, but in doing that, you're also giving your models, which is presumably your contribution to the field.
I guess, but that's why I'm contributing so other people can use it. I'm not talking, I guess it'd be different if you're patenting things. I'm certainly not patenting anything, right? And that is its own. So one of the people last time he gave this presentation said, okay, what about intellectual property rights? Like, where does that fit in? And that is part of this discussion. And I think, at least my observations is also, I think there is a generational change. I find the older generations are much more wary about people basically stealing, and scooping, because I suspect it may have happened. Whereas I think some of the younger generations are a little bit more, just let's put it out there and see what happens.
So with that, follow-up to it was when you're involved in a collaborative project, you have 8 people and one is an old guard that doesn't want to do that. And
Yeah.
is that better, Chris?
Yeah, so-
Pam's motioning behind me to tell.
Yeah. So you make a really good point. So working collaboratively can raise some challenges. If I'm the lead, I'm certainly going to push it very hard. But if someone's dead set against it, like they would have to give me a pretty good reason for me not to. I usually find the arguments oftentimes not very good, right? They're just like, well, what if this and this and this happens? And I was like, well, it's probably not. And if it does, everything's open. Our names are on this. So someone's going to copy us and scoop us. Like, we'll know. And it's clearly ours first. Because I even remember someone telling me the best way to get scooped is to post it, put your name on it, and make sure the attributions are there. Give it a DOI. You can copyright stuff like, that script, it has an open use license to it. So that's the way to do it. But again, you always run the risk. And I'm personally not that concerned about it.
Thanks.
Yeah.
All right, thanks.
Mazar, go ahead.
Thanks, Alex. I really appreciate a lot of what you said. We've spoken before, I like boss software.
Yeah.
And I teach it in my research methods whenever I can.
Yeah.
Priority, here, you can get this for free, and it's not that easy.
Yeah.
It's not that hard. And in fact, sometimes it's easier and better. My question is kind of related to that is, sometimes it's something in proprietary software which is not available in free and open source. How have you managed that friction? And then the second question is about the hardware that you might use. It's obviously hard to develop open source software hardware.
Oh yeah.
So-
Okay. So the first one is about right, if there's not an open, free, available alternative, or the open and free alternative isn't as good as the proprietary version. So in my own work, where I come up, most of that is a lot with the GIS and spatial stuff. Because a lot of people want to use ArcGIS and ArcPro. There are alternatives. So I think QGIS? There's Grass. I think is another one. And I don't know how to really use any of them. So it's usually what my collaborators will do, because I'm certainly not going to tell them to go learn QGIS or Grass. when they are already proficient in these things. And so I don't really have a problem with it. And again, I think for me, it's just like, I think I want to make sure that we have the methods detailed enough that someone could actually go in and use it. So that would be the way to do it, is just have better descriptions of your methods. And all those little kind of seemingly insignificant steps probably should go in your methods. And again, this is where I think supplementary materials are just a fantastic addition, because you can put it all in there. Great, because a lot of times you develop these methods and whatever else for your research group, and so your next grad student is going to use the same thing anyway. So you may as well have it written up, and you may as well put it attached to the paper anyway, because why not? So the next one was hardware. So I've never actually, well, I mean, trying to think of. Oh yeah, so I guess so. You're talking about like your operating system. So you're talking about like an instrument that I made myself, like.
There are some tools where farmers have kind of developed themselves and showcased it on kind of like farm hack, like, hey,
Yeah.
you can do this tiller or.
Yeah, so if you look in the literature, at least where my field is, there are lots of method papers where people have built these things that don't use electricity because they need to hike it up some mountain or something like that, right? And so a lot of them are, I call them hardware store science, because they are made from stuff from Home Depot, right? And they often work just as well as more complicated ones. So that's one way to do it, is actually publish methods paper. I was talking to an editor-in-chief kind of about this, and he was saying that a lot of journals don't like methods papers because they're not very exciting, they're not very sexy, but they're really, really important. And so as a subject editor, I was kind of encouraged to like have a read through this. Don't just disregard. I'm completely on board with it, and I'd actually probably like to see more of these types of papers, but they're hard to find a home sometimes. If you're making your own like models and things like that, there is a place like the Journal of Open Source Software. The ROpenSci has a peer review. They'll peer review your package, right? And so even your code goes through peer review. So if you're building some type of statistical model, we'll have someone look through and make sure you didn't actually make any mistakes, and make sure that it works as intended. And so there are definitely ways around it. Yeah.
Sounds like you need to start your own journal called Methods in Science, and it'll just be method papers.
Well, yeah, for sure. I mean, isn't there like, I feel like someone also had like the Journal of Non-Results or something like that. Negative results or something like that, right? For all these kind of like failed experiments where you put in all this work and you said, oh, well, doesn't matter, or like.
Yeah, Dion and Brian have been talking about the Journal of Failed Experiments for a
Yeah,
while.
just think how much you could probably learn from those failures, right? Because you're just like, well, you already know that this doesn't work. I don't know it doesn't work, so I'm going to actually try it. And then
yeah, the
fail
peer
myself.
review would be really interesting, right? Because it would have to be like, yeah, that might have worked. Now that I know that it doesn't, is it obvious before or after, right? But my question was about the MATLAB script that you didn't. I'm gonna say copy,
yeah,
because it kind of serves the point of my question, right? So if you do have proprietary code that you're then trying to make open source, like I'm guessing that guy's MATLAB code was his own IP,
yeah.
which he shared with you, so not a problem.
Yeah.
But what happens when you come across code that is proprietary, but you do want to essentially hack it and do it in R?
I mean, I would probably just approach the owner. Because presumably if they're making the code available, they're assuming that people will modify it.
Yeah, perhaps.
So I'm not entirely certain I know the answer to that really well.
Yeah. That was your question as well.
So I have a quick question. I work like with Doug, work social science mostly, and I don't have millions of lines. So I've got maybe a couple hundred cases or something like that. But I do all my work in SPSS.
Yeah.
So if I was to upload that, what format is all that data in that you've got in all those open? Is like CSV?
Most of it's just CSV. Yeah.
So you could export it from SAS or SPSS as a CSV.
Yeah. So I often.
And then
yeah. So in R, like you can, like I said, the data is just often CSV. If you want to publish reports and stuff like that. So that report that I sent from my colleague, that was just actually an HTML file. You can also export it as PDF or whatever the case may be.
Okay.
So there's different ways. So that's one thing that Quarto is kind of a neat integration between writing and documenting and doing science. So like, because you can hide a lot of the background stuff if you don't need to show it, right?
Right.
And whatnot, but it's all there.
Because if you export an SPSS, you lose all the metadata. If you just export it as CSV, you're just going to have the data. You're not going to have
all these steps in between.
Yeah.
So yeah, I'm not familiar with it, so I don't really know whether you can just export the whole thing as a giant text file.
But for example, all the variable names and everything, that's all in a different tab, and that wouldn't get, so you wouldn't know what the variable names of all the different codes were.
Yeah, and I think this is where some programs lend themselves a lot easier than others. And that's just the nature of these things, right? And so maybe for your case, you would have to export them separately or whatever. I don't really know.
I'm going to give one more question to the floor, and then we'll have
I got a comment from online too.
a comment to an answer or a question.
I'll just read the whole thing.
Okay. Do you want to go first, Stephen? And then
I'm here.
Oh, okay.
If I can do that,
Oh,
then I'll
okay. He
get to
doesn't have a
Stephen.
mic. Okay, sorry.
Okay, apologies. So Michael's question, if some other people are able to take your shared scripts and then convert them into executables or extensions that they are able to monetize, would you be able to claim royalty or accept that Christmas came early for those people?
Well, that might violate the license I have on it. So in which case it would become a legal matter. I mean, for most things I do, like, as long as my version stays free, I mean, nothing I think also in my case, like, nothing I do is worth any money. Like, no one cares. Let's be honest. Well, I mean, yes and no. I mean, you can go to the website and do it for free. So, and again, you can also make your own and access their API or whatever and do it. So, but yeah.
Good.
Okay, thank you. This is a
Hold it
topic.
up. Hold it up.
This is a topic that's huge for me in computer science. When we publish a piece of software with an open license, that forces anything that's derivative from it to copy and include your open license. So
Right.
if I use an MIT license, say,
Right.
anything that comes from that is constrained by my license to include open source. SAS, SPSS, or these other, like, say, Pix40, these mapping, this geospatial data, or proprietary stats, they're often made difficult to export from. The opposite of forcing openness is obfuscating everything, and they make it extremely difficult to export from. And that's one reason to get away from to try to include open source in whatever you do, because it sets everyone downstream from you free. And what's the result of that in computer science has been exponential growth. The speed at which comp sci is moving right now, with even our peer review processes are happening like on the preprint servers. That's our base point.
Right.
It's happening so fast that we can't publish fast enough. Like, it's orders of magnitude. And you guys were talking about, hey, there's these companies that, like SPSS or proprietary stats, that aim to obfuscate openness. And once you have this open source kind of collective action on a piece of software, it can move so fast that profitability isn't a question. Like, for the people who want to stay closed source or to not enter that kind of mode, the speed at which, like, you can produce value so fast, even with the IP wide open, that you just can't touch it. Like, there's lots of criticisms against it, but, like, I don't know, I'm just trying to add to it from my perspective. Like, this is the core of computer science.
Yeah, and so one thing I would like to see more of is people and organizations funding open source software. I can tell you the creator WeatherCan has not made a cent on that.
Right. This is a huge.
That was a personal bit of a passion project, a little bit of a showcase of their abilities. So it has kind of tangentially resulted in income and stuff like that. But, you know, an organization like our OpenSci, right, it relies on grants and things like that. And it's hard to, even for me, I get a salary. So it's not so, if I spend time creating something, whatever, I collect my salary whether I do or don't. But for someone who's not in a position like mine, why on earth would they ever do it other than the fact that it's just awesome? And a lot of people do it just because it is awesome and they're just super nerdy, and like, why wouldn't they? So
it's monetizing open source has been an issue.
Yeah.
But Linux has been free for 20 years.
Yeah.
And it's the leading it's the leading
Yeah.
it's the leading operating system for all major infrastructure.
Yeah.
And billions of dollars have been made to programmers to work on it.
Yeah.
So like
It can be done.
It doesn't seem like there's not immediate benefit for a programmer or a scientist to take this mode of operating on, but collectively it does produce enormous value downstream. Even like, so let's say your whole science like my hardware is open, my software is open, and yet I'm still able to monetize things because the synthesis of all of that is something like anyone can pull my tools.
Right.
But the synthesis of it is something that only a few people can actually draw together.
Right.
But anyone can add to.
Yeah.
So it's a modality that only moves up. Sorry, this isn't a question. I just it's the core of comp sci.
Yeah.
And its results are I can't keep up. Like no one can keep up with comp sci right now. You can't read fast enough.
Oh yeah.
And and that's all happening on open preprint, open. I can go and peer review like George Hotz. I can go peer review right now as an undergrad student, leading AI ML papers right now on a preprint server. They're publishing stuff. Meta, everything is open source. Everything. Multi-terabyte data sets. It's all open source. $1 trillion company. Why are they worth $1 trillion with everything open? Because they can synthesize it.
Yeah.
But everyone's adding to it. So
You guys should go for a beer.
yeah.
Totally. I think we're gonna move on a little bit. Pam has a question from online.
Yeah, Alan has a couple of questions. I think we will have
I think
to
this will
wrap
be
up
the
to
last
this.
question because we're right at 3:30.
But obviously you're welcome to stay and talk to Dr. Koiter. So first kind of question, please comment on the importance of controls and experimental research, and then a few follow-up comments that I think we're stemming out of some of Stephen's conversation. Some statistical GUIs such as JUMP and Systat produce scripts, and know the companies like SAS and Systat do obfuscate openness. The coder script is still there, not obfuscate. Yeah, sorry. He's just on the fly correcting.
Okay.
So companies like SAS and Systat do not obfuscate openness.
Yeah.
The coder script is still there.
Yeah, in
So,
SPSS, the code's there. You can actually code it underneath it.
exactly. Yeah. So yeah, if you're willing to, maybe briefly give some thoughts on Alan's thoughts.
So you talk about control and experimental design. So I guess I'll go back to my first point. Like a study can be awful and still reproducible. They are two separate questions, but they are kind of intertwined. So I think one nice thing about being open, it's a bit easier to see how people have actually done things. It's like you can say, oh, do they actually have a proper control, or like at least in their data. But in of itself, being reproducible and open doesn't necessarily mean you're going to have the best research design. It just means people actually be able to see what you've done. And I think that's really the big point, because you can look at my studies and say, oh, Alex, you didn't put a control. I'm not going to really buy into your results very much. And that is fair. I've told you exactly what I've done, and you can draw your own conclusions about the quality of my work. And I think that's where the really strong thing is. Or you can pull me aside and say, hey, you can make this even better by doing this. I can say that's great. Let's collaborate and do that. But again, you only really kind of know these things if you are as open as you can and reproducible as you can. So, any other comments? Can't remember. All right, good.
Okay,
Thanks,
thank
Alan.
you very much, everyone.